Welcome, ladies and gentlemen, to another video on shellcode for the ARM64 architecture. In previous videos on this channel, I showed you how to write shellcode for macOS on M1 chips. And in this video, I want to show what is necessary to transfer this shellcode to other ARM64 operating systems, namely FreeBSD and Raspberry Pi OS, which is an ARM64 Linux. And I will only show this for the reverse shell. Once we know which changes are required for a reverse shell, it should be easy to also transfer a bind shell to the other operating systems. Before we continue, please take a moment to like this video and subscribe to my channel. The more support I get, the easier it will be for me to produce videos in the future. Thank you. So this video has two parts. One in which we transfer our macOS reverse shell to FreeBSD, and one in which we transfer it to Raspberry Pi OS, both also on ARM64 architectures. And in both parts I will quickly talk about the environment and which tools are required. Then I will recall the structure of the reverse shell and review which changes are necessary to adapt the code to FreeBSD or Raspberry Pi. First, I want to quickly look at our macOS reverse shellcode to remember what it consisted of. So here we have it again. You see we had 4 main steps which correspond to 4 system calls. So the first one is the socket system call, where we create a socket for the communication to our attacker machine. Here we set up the parameters for the protocol family, the protocol type, and a third redundant parameter. And then we use the supervisor call to actually execute the system call and create a socket. Then we connect this socket to our attacker machine's IP address. So we set up this sock adder in structure here in the register X3. So we had this redundant field synlen, then we again put the protocol family in there, the port for our communication, and the IP address of the attacking machine. And recall that we have to use the big endian convention when we are dealing with the internet protocol. Then we put all these arguments on the stack and put them in the appropriate registers and execute the system call for connect, and thus establish a connection from the target machine to the attacker machine. In the next step, to redirect input and output from the target to the attacker, we duplicate the file descriptors for standard input, standard output, and standard error. And we had the dup2 system call for that. And we call it 3 times for each of those 3 here. And finally, once this is done, we launch a shell, and we do this with the system call execve, and we give it this argument here /bin/zsh for the Z shell, which is the standard shell on macOS, and give it its standard argument, which is just the path name for the executable again. And then we do the system call for execve, and this starts the shell in the process that runs our reverse shell, and input and output for the shell will be redirected to our socket that we created in the first step, and thus will be redirected to the attacker machine because we connected this socket to the attacker machine. If you want more explanations on this, I recommend you watch my videos on macOS shellcode. Now let's turn to FreeBSD first. To test FreeBSD on an ARM64 architecture, I installed it on a Raspberry Pi. And it's surprisingly easy to do that, and I will not go through the process here, but I will put a link in the description box that you can follow if you want to install it on your own Raspberry Pi. Once FreeBSD is up and running, we must make sure to have the proper developer tools on the system. So for this, you have to install the packages LLVM and binutils. So binutils are the GNU developer tools, and these are the LLVM developer tools. And for this, you can use the pkg command with the install option and the packet name. So we get the Clang compiler and LLDB debugger, and in binutils we get the assembler AS and the GDB debugger if you prefer that one. And since macOS is also a BSD-based operating system, it's reasonable to expect that our original shellcode will run with little changes on FreeBSD. And first, I want to confirm the system call numbers. We can look them up in this file on our system here. So we look at the file /user/include /sys/syscall.h, and here we find a lot of macros for the system calls with their corresponding system call numbers. And if we scroll down a little bit, we will find execve with number 59, same as on macOS. And still a bit further down, we will find dup2 with system call number 90, and we will also find the internet system calls socket and connect with numbers 97, 98, also the same as on macOS. So, not much to our surprise, we find that the system call numbers in FreeBSD are the same as in macOS. 97 for the socket call, 98 for the connect call, 90 for the dup2 call, and 59 for the execve call. Here are some changes we need to make for our shellcode, and well, these ones are either self-evident or they're very easy to Google, so I'm not going into where these come from. The first one being that the program entry point must be labeled by _start and not, as in macOS, by _main. The system call numbers are not stored in x16, but they're stored in the register x8 on FreeBSD. And because we're using the GNU AS compiler, we have to change our source code comments to the C style // and we cannot use the semicolon. And of course, because I'm using it on a different machine, not on my personal Mac, but on the Raspberry Pi, we have to change the IP address for the connect call from my Apple machine to my Raspberry Pi machine. And finally, we need to change the shell that is to be run by the execve system call, because on macOS we had the default Z shell, but this is usually not installed on Raspberry Pi, so we go with the default bash, which we can find at /bin/sh. Once these changes have been made, we can test our reverse shell as usual. So we assemble with this command here, as reverse shell.asm-o reverse shell.o. Then we have created this object file. We link with the ld command, reverse shell.o-o reverse shell. And note that other than on macOS, we do not need to provide a library path here, so this is actually a bit more convenient than on macOS. And then we start a netcat listener on port 1234. and C-L1234 and run our reverse shell. So here I am with my macOS shellcode in mousepad on FreeBSD, and now I want to make the necessary changes to make the shell run on FreeBSD. So first I changed the name of the program entry point to start. Next I will change the register, which holds the system call number from x16 to x8. You can do a search and replace to change it in all occurrences. And now I will change the comment signs from the semicolon to the C-style double slash. Also one search and replace to do them all at once. Now just fix the layout a little bit. And next I will have to fix the system calls. For connect, I need to find out the IP address of my Raspberry Pi, so I can use ifconfig for that and just grab the IP address. And here we see it's 10.0.0.4, so I changed that in the source code for my reverse shell. Here in the sock_adder_in structure. Okay, and now I need to change the shell to the bash, because as I said, that shell is not available in FreeBSD. So I use /bin/sh and I add a null byte at the end to terminate the string. And I can also change it directly here in the register x3. Yeah, that should do it. So I made the changes necessary. Now I have my netcat listener running here, and I will assemble and link my reverse shellcode and see if it works. Use AS for assembling, then LD for linking. And run the shellcode. Oh, what is this? This should not have happened. Our binary is broken. Well, that did not work as expected, did it? It turns out that on FreeBSD, the AS assembler does not seem to produce the correct kind of binary format. To fix this problem, we can use the Clang C compiler as an assembler with the following command: cc -c reverse shell.asm. Now with the -c option, the C compiler will automatically produce the .o file for reverse shell. We don't have to use the -o option here. And yeah, it will produce assembly output. And another problem that would arise now, but I'm just fixing it in the same go here, is that FreeBSD actually requires our supervisor call svc to have the argument 0. Recall that on macOS this argument was ignored and we could choose it to guarantee that our shellcode is free of null bytes. But here we have to use 0 as an argument for the supervisor call. And unfortunately, due to this requirement, we cannot avoid having null bytes in our shellcode when we use system calls. So let's make these changes and try our reverse shell again. And here we are back in Mousepad, and I will change the arguments for the supervisor calls to 0 in each case. So that should make our reverse shell work on FreeBSD. Now let's try it out, and this time I will assemble my file with the C compiler using the -c flag. And here I do not have to specify an output file, as I mentioned before, because it will be automatically written to reverseshell.o. Now I link this file to get my executable. And I restart my netcat listener before I run the shell. And hope that it works now. So let's see if we can execute commands. Yes, we can. Wonderful. Our reverse shell on FreeBSD works. So let's see now how we're doing with null bytes. I mentioned already that due to the system call argument 0 that we have to pass to the SVZ instruction, we will automatically incur some null bytes, and we can't really avoid that. Oh, that's a bit much. Let's filter out the null bytes. Okay, that looks like a lot, but this is actually just due to the output format of object dump here. Because if you look closely, then you will see that most of these null bytes actually are just 2 zeros that go over byte boundaries. So actually the bytes here are this and this and this. So the 2 zeros here do not belong to one and the same byte. They're no proper null bytes. But of course here, for our supervisor instructions, we see that we actually pick up a lot of null bytes. So as I mentioned before, this can't be avoided. We have to live with it. That concludes the part on FreeBSD. And we now turn to adapting the reverse shell to Raspberry Pi OS. Raspberry Pi OS is the official operating system for the Raspberry Pi. And it was derived from Debian Linux and comes in 32 and 64-bit versions. And since the Raspberry Pi is based on the ARM64 architecture, we can use it to try to transfer our shellcode to the Linux ARM64 world. And given that Raspberry Pi OS is the official operating system for the Raspberry Pi, it should not surprise us that it's rather easy to set up. The developer tools can be installed with apt install binutils, similar to what we did on FreeBSD, only here we use the apt tool, and this contains the GNU developer tools, including assembler and linker. First, we need to find out how to do system calls in Linux. So Linux is not the same as BSD, so we have to be prepared that there will be some differences. And there's actually a man page for system calls on Linux that will tell us about the calling conventions. And for the system call numbers, we can look into this header file at /user/include/asmgeneric/unistd.h. So here we are on the Raspberry Pi, and I will first look up the man page for the system calls. If we scroll down a little bit here, then we find the calling conventions for different architectures. And we are of course interested in the ARM64 architecture. And what we see here is that the register to hold the system call number is W8, which is just the lower 32 bits of X8, so we can just use the register X8 to store our system call number. What we also see here is that SVC is supposed to be called with argument 0, as it was on FreeBSD, but it turns out that on Linux you can also just give an arbitrary argument to SVC, so we can just choose a value that avoids null bytes in the binary encoding. And we also see that the return value is stored in the register X0, and if we scroll down, we find that the arguments that are passed to the system call are, as we expect, stored in registers X0, X1, X2, and so on. So the calling convention is almost the same as on macOS, except that we use X8 to store the system call, and now we will look at the file /user/include/asmgeneric/ unistdh, and here we have the system call numbers for Linux, and they are different than the ones on BSD or macOS. So let's search for the system calls that we're interested in. First, the socket system call. So we see this is 198, and a little bit below it we see there are also the other internet system calls, especially the connect system call, 203 on Linux. And now we scroll up a little bit to find the dup2 call, but actually we find dup2 is missing on Linux. We have dup and we have a new call, dup3. So that could be a problem. We have to look into that. And finally, we want to know the number for our system call execve, which we find here, and it's 221. So yeah, we could look up the system call numbers in this file, and now we investigate what is it, dup3. So the man page still lists dup2, but there was no system call number for it, so we can't expect to be able to use it. And if we look at what dup3 does, it says it is the same as dup2, except that in addition we have a flag argument, a third argument flags that we can hand to the system call. And that's good, so basically we can use dup3 just like we use dup2. Our reverse shell still has the same general structure, but we need to make a few changes. We need to change the system call numbers to the ones for Linux, so I've listed them here. And in the connect call, we must adapt the sock_adder_in structure for the second argument to this call. And we must replace the dup2 system call, which doesn't exist on Linux here anymore, by the dup3 system call. And I will quickly take a look at those two system calls here to make clear what we need to modify. The declaration of the connect system call is the same in Linux as it was in BSD or macOS. But the second argument, sock_adder_in, is a structure that holds the information for the internet connection we wish to establish. And on Linux, it looks differently than on BSD. But first recall what it looked like in BSD or on macOS. We had these fields here that make up the structure. So 1 byte for sin_leng, which is an unused field, 1 byte for sin_family, 2 bytes for sin_port, 4 bytes for the IP address, sin address, and then 8 bytes just to fill it up to a total size of 16 bytes. And if you've watched my videos on macOS, where I already mentioned that the Linux structure is different, then I told you there that the synlen field is missing. So what does it look like with the missing synlen field on Linux? To find that out, we take a closer look at the structure, and we can use the following sources for that. So the sock_in structure is defined in /user/include/net/inet/in.h. Alternatively, we can look it up in the man page IP. And in this file, it refers to a data type SA_family_t, which is not defined here, but rather in this file /user/include/AR64-linux-gnu/bits/sockadder.h. And we'll have a look at this now. And first we're going to look at the file /user/include/net/inet/in.h, and here we have all the data structures required for the Internet Protocol. And we can search for the sock_in structure, and we find it here, and underneath the corresponding structure for IPv6, but we're not interested in that. So this is the structure we care about. And we see the fields are there, the sin0 padding to pad the size of the whole structure to 16 bytes. Then we have 4 bytes sin adder for the internet address and 2 bytes for the port. And here in the beginning, we have as first entry this somewhat mysterious sock_adder common macro. And this is where it differs from the BSD structure. So we will have to look into that, how this is defined. And after a little bit of searching, we find that this structure is defined in /user/include AR64-linux-gnu/bits/sockadder.h. And here we find the macro sock_adder common, and it is basically a wrapper for this data structure or data type SA family T. And this one is defined up here as an unsigned short int. So that means it's 2 bytes large, which means it's actually twice as large as it was on FreeBSD or macOS. And of course that changes a little bit how we have to store the data in our sock_adder structure. So to sum up, this is what the sock_in structure looks like on Linux. So it's almost identical to the BSD one, only that here the sin family field has swallowed up the sin length field. So this is now 2 bytes in size instead of 1. And as I just mentioned, we need to be careful how we store the value that we write into the sin family field. It actually has to go into the lowest order byte of this whole structure rather than of the second lowest order byte as we had to do it in BSD. And the other arguments stay the same as we had them on macOS, so no changes here. We also saw that the dup3 system call is almost identical to the dup2 system call we used on macOS, only that we need to provide a third argument, flags. But this one we can just ignore and set it to 0. We just have to provide it. And the first 2 arguments, fd and fd2, have the same meaning as for the dup2 system call in macOS, namely the file or socket descriptor being duplicated and the descriptor which it is duplicated into. And now we can make the following changes to our reverse shellcode to adapt it to Raspberry Pi OS. As on FreeBSD, we have to change the label for the program entry point to _start and not use _main. And again, we need to change our source code comments to C style, / and not the semicolon. Also, as on FreeBSD, we use the register x8 instead of x16 to store the system call number. And we replace the BSD system call numbers by the Linux system call numbers. Then we need to modify the sock attr_in structure for the connect call. And that includes changing the IP address, again, from my Mac machine to my Raspberry Pi. And again, as we did for FreeBSD, in the execve call, we do not call the Z shell because it's by default not installed on Raspberry Pi, but rather we use bash, which we find at /bin/sh. And once we've done this, we can do the usual to test our reverse shell, as reverse shell.asm -o reverse shell.o, then link it. Again, as on FreeBSD, we do not provide any libraries here. ld reverse shell.o -o reverse shell, and then we start a netcat listener on port 1234. And on Linux, we actually have to include the P option in netcat, nc-lp 1234, and then in a different terminal, we run our reverse shell to find out if it works. So here I am on my Raspberry Pi again, and this is the original macOS shellcode, and I will now change it to make it work on Raspberry Pi OS. So the first thing I need to do is to change the start symbol from _main to _start. Next, I have to change the comments in the source code. I cannot use semicolons, but I have to use C style /. And then I have to change the register that holds the system call number from x16 to x8 in all cases. And now I have to replace the BSD system call numbers and the BSD system call dup2 by the Linux system call numbers and the Linux system call dup3 respectively. So for socket, I now use number 198. For connect, I will use 203. And now I have to change the dup2 system call to the dup3 system call for Linux. And this one has number 24. And here I actually forgot to put the third argument for dup3 in register x2, but I'll do that in a moment. And finally, the execve system call is 221 on Linux. And the next thing I do is I fix the sock adder in structure. So because we are on Linux, this synlang field does not exist. So we remove it here in the commentary. And we have to put the value 2 for our protocol in the lowest order byte of the sock adder in structure. So we make that change now. And this is how it should work. And now we need to change the IP address to my Raspberry Pi. So I have to look up what my IP address is. And we find it to be 10.0.0.1. So we put this into the shellcode. And now instead of calling the Z shell, which is not installed by default on Raspberry Pi OS, we have to call bash. So we change the argument string for execve to /bin/sh, and then we add a null byte to terminate the string. And that should call the correct shell. I fixed it here in register x3. And now what remains to do is to fix the third argument for the dup3 call, which is simply 0. So we ignore the flags argument, but we have to pass it anyway. And I repeat this every time I do the dup3 system call, because I cannot be sure that the register x2 will be preserved by this system call. Okay, that should fix our shellcode, and now I will test it. Start netcat with the -lp option. Remember, on Linux we have to use p. And now I will assemble and link my shellcode and see if it works. We run the reverse shell. Now check in netcat. Can we execute commands? Yes, great. The reverse shell works. And we can execute commands in netcat. And that concludes my video on shellcode for FreeBSD and Raspberry Pi OS. Once more, please like and subscribe and stay tuned for more content here.